Our next speaker is Alyssa Ross from Manifold 3D. She's CEO. And this is a Toronto-based startup focused on unlocking lattices, microstructures, and metamaterials in large build volumes. She holds a PhD in discrete geometry and has worked with Mesh Consultants Incorporated as an industrial mathematical consultant on interdisciplinary projects since 2014. We're so excited to have you, Alyssa, to learn about this very interesting topic. The title is Why Surface Area Matters, Challenges and Opportunities of 3D Printed Metamaterials. Alyssa, the floor is yours.
Awesome. Okay, thank you so much for the introduction, Amy, and thank you for the opportunity to stay. I'm very excited to be here, and I really appreciate the impeccable organization of this whole conference. Now, before I share my screen, I don't know if you can see my video okay, but I did want to just set the stage for what I'll be speaking about, which is metamaterials. So I want to use an example, which is just a piece of paper. My paper has math on it, of course, but it's just a piece of paper. And we all know the material properties of paper. It's floppy, it's not rigid, all these kinds of things. But what we can do is we can introduce some geometry. And like a cooking show, I have this prepared. I've put a little accordion fold into my piece of paper. And now my geometry has a new, or sorry, my paper has a new property, which is that it can actually stand up and be, well, more rigid than it was before anyway. So the point is, we haven't changed the material, but we have changed geometry. And that's really at the heart of the idea of metamaterials, which is what I want to talk about today. So just bear with me while I share my screen here. Okay. All right, great. So hopefully that looks okay. So as Amy mentioned, I'm a mathematician. I have been interested in the connection between geometry and materials for a very long time, and in particular, the way that geometry contributes to structure and performance of materials. And that's really at the heart of the idea of 3D printed metamaterials. So today I want to tell you about challenges and opportunities involved with 3D printed metamaterials with a focus on surface area. Okay, so as an outline, I'll start with a little introduction, a little more elaboration on what metamaterials are, talk about the challenges, and then give some, hopefully, an optimistic conclusion about some new approaches and opportunities for moving forward. Okay, so I know there have been some amazing talks in this session about metal printing and about the microstructures of metal. I want to use a slightly probably different definition of microstructures, which is maybe a little bit looser, so it's not tied to any particular skill that you might observe, say, with a microscope, but rather I want to think of microstructures as defined by two key principles. The first principle is this idea that the small scale architectures modify the macro scale behavior of an object. So the examples on screen here are wood. This is actually a good example. The cellular composition of wood gives wood its characteristic behavior. We all know that if you cut wood with the grain, you get a different performance than if you cut wood against the grain. And similarly, the structure of bone, our bones actually form in response to forces on the bones, and they, it's a kind of a natural topology application where those microstructures develop in response to putting matter where it is needed most. So that's the first principle. And the second principle is this idea of separation of scales. And I really want to conceive of microstructures and the mechanical behavior of microstructures as the average behavior of a sufficiently large volume that is filled with those microstructures. So you can think this as in this part here, the lattice units, these little beams are very small relative to the size of the overall part. Or if you like the schematic, this little dot here is the microstructure, and it's very, very much smaller than this scale, than the macro scale, than the scale of the overall part. So these are the two key principles that I want to focus on for microstructures, separation of scales and the micro scale impacting the macro scale. Now, I need to talk a little bit about homogenization and the motivation for thinking about that separation of scales is in part due to the idea of homogenization, that when we're working with lattice geometry, for example, so lattices are a type of metamaterial. When we're working with lattice geometry, a lot of the time we get sort of stuck. I don't think you can see my mouse. So we get stuck on the left-hand side, where we're really viewing that lattice as a structure. And if we wanted to do any kind of simulation on that, we would probably need to mesh it and do our finite element analysis on that. And anyone who's tried to do this with any quantity of lattice whatsoever knows that this is a huge headache and it's very difficult. And the point is that we can achieve uniform material properties by miniaturizing those lattice units so that they, again, become very small relative to the overall size of the volume being considered. And so this is the key idea that, that I'm interested in, is this idea of lattices and metamaterials as actual materials, where we think of them as actually having material properties. And when we do that, we're able to set in the context of other materials. And to give you a sense of why we might care about this, this is the material property space measured on strength versus density here. And so you have, metals, polymers. I'm sure many of you are familiar with these kind of pictures. And those very long finger-like regions there are actually lattices. So if you see the origin of them, they originate on aluminum and carbon fiber reinforced polymer. And the long finger region is extending into material property space as a result of variations in geometry. So again, varying the geometry, we get to obtain different material properties. And so that's really at the heart of this idea of mechanical metamaterials, that we can vary geometry to get really remarkable properties that actually go beyond what we find in nature and chart new territory in material property space. So when I say metamaterials, lattices, microstructures, I just want to throw this slide up. There's so many different terms that get used. I want to speak about the whole kind of area of these kinds of things, sometimes called architected or engineered materials. And these can take a whole bunch of different forms. They can be cellular or kind of random in the case of foams or other stochastically generated geometries. Very frequently, we see these slender beam topologies or beam-based lattices, truss-based lattices. This is often what people mean when they say lattice. But then there's also this emerging family of smooth topologies, surface-based lattices, shell-based, and triply periodic minimal surfaces, which are enjoying a kind of moment of popularity right now. Okay, so I do want to mention a few applications. So hopefully, you've got a sense of what metamaterials are. And I think we've all probably seen a lot of applications of metamaterials already. Certainly, footwear and helmets. Metamaterials are used a lot for impact mitigation, which is why they come up so much in sportswear. And I think those applications are super cool. I've been working on those applications for a good number of years, so I really like them. But today I actually want to focus on a different set of applications, which are maybe less well known. And these applications really come from this area. So in this first set, I have carbon capture and filtration. So on the left here is a recent paper out of Livermore National Laboratory on cellular fluidics. This is basically like a three-dimensional microfluidic design where they actually use open cell microstructures to control fluid flow. This is a super cool paper. And one of the interesting applications there is in carbon capture. And the reason is that they are able to expose a whole lot of air to liquid sorbent. So the air contains greenhouse gases, and by exposing more of it through more surface, you're able to capture more greenhouse gases from the atmosphere, which is very cool. Similarly, this carbon capture device, this is a carbon capture device that involved a heat exchanger. And the last application here is in filtration, environmental filtration, where the geometry actually controls microorganism growth. And the higher the surface area, the more material can be filtered out of the water. The second of applications is in heat and energy management. And again, I think probably many people have seen heat exchangers that have been produced through 3D printing. And these are is a great use case for 3D printing. And it really, again, comes down to surface area. That the reason those heat exchangers are so successful is that there's more surface for those two different temperatures to come into contact with each other over. And similarly for batteries, I think there's a really exciting opportunity in batteries because you have this possibility by increasing surface area of increasing the energy flow between the two parts of a battery. So those are just a sample of applications, and hopefully I've convinced you that metamaterials are cool and we should be thinking about how they apply. But I now want to talk about some of the challenges. So I'm going to identify 3 challenges. The first is in exploration. And I find that often when people encounter lattices and 3D printing, they want to jump right on and print some lattices, which is cool. But actually, how do you find the best lattice or metamaterial for your particular application? And this is kind of a more challenging problem than you might think, because the space of lattices is infinite. And how do you actually find the best one? So that's really the first challenge. The second challenge is just complexity, that these are incredibly complex forms, many intricate details, and very high surface area. So this makes things like capturing them as a surface presentation, like a triangle mesh, very unappealing. It's something you can only do if you're looking at very small quantities of lattices. And then finally, scale. So actually manufacturing these things. So many, as I just said, many AM processes actually require that surface representation, which is then sliced and sent to a printer, which create a computational bottleneck. So how do we actually communicate these lattice geometries in a better way to printers, to the hardware? So I could sum it's a little oversimplified, but the way I see it is that 3D printing is really good at the moment at producing large parts, or it can produce, on the other hand, it can produce small and detailed parts, but it doesn't do both at the same time. It doesn't put very large, very detailed parts. And I do want to mention that this is really not a very large part at all. I saw a great talk yesterday about someone printing parts that are as big as a ship or a army vehicle. So really, how large can we go, and also how detailed? So what is the resolution, size, trade-off, and does there need to be a trade-off? So the result of this is that in my experience, there's really a limited use of metamaterials in industry. And so we see projects like this one, which I, again, think is a super cool project, but it really is still in that lattices as structures regime, where these are large lattice elements. We're not really viewing the lattice as a homogeneous material. We're viewing it as a structure, and it can give some nice properties, but it's really still in that structure area. In addition to that, a lot of the research has focused on, and the implementation has focused on, only a handful of representatives of different metamaterials and lattice types. And this speaks to that exploration piece, that it can be hard to find the right lattice or new lattices to meet your needs. So I do want to talk through some opportunities, an outlook here on how we might think about using metamaterials in an industrially relevant way. So the first is on that exploration piece. There have been some really interesting work in trying to solve this. So actually, the first one I want to talk about is something, that I worked on. So this is a paper I wrote with my colleague Daniel, where we trained a graph neural network on lattice geometry to predict compression stiffness. So this is really nice because it means that if you're a designer and you're trying to work with a lattice, you don't actually need to run simulation on the whole thing, but you can actually experience in real time using that trained model whether your changes are causing the lattice to become more or less stiff relative to a particular force. Then moving to work that is not my own, but I think is super cool. So this is out of the ETH in Zurich. These are called Spinoid Topologies. As you can see, they tend to be kind of bone mimetic. But the authors of this paper basically created an inverse machine learning model where you would specify the performance characteristic, in this case, a stress matrix, and the machine learning model would actually return a spinoid topology, or really the design parameters spinoid. So this is really cool, and it was really kind of the first instance that I was aware of an inverse model predicting metamaterial geometry. And on the right here are some samples that we printed of these forms. Sorry about that. And then a second paper, also out of the ETH in Zurich, basically did the same thing, but for truss lattices. And here you specify your stiffness tensor, and the machine learning model will generate geometry that meets that that target. So this is a really, again, a really cool way of working, that if you know the performance characteristic and you're okay with it being from one of these limited families of topologies, then you may have a solution. So, and again, on the right is just some lattice sample that we printed at Manifold. So let me actually move now to what we do at Manifold and how we use some of these ideas. So our big thing is to address both of these challenges, the exploration challenge and that complexity scale challenge, through new manufacturing methodologies. So the first part is like an exploration tool where we have a cloud-based lattice and MetaMaterials app. This is also a cloud-based slicer. So we have a curated set of lattices from that cover a spectrum of different material behaviors, and that are really based on those material behaviors are based on the idea of achieving length separation. So this is our web app, but this is really powered, sort of once you've got your lattice geometry, this is powered by what we're calling geometry streaming. And this is where we're taking a very hardware first approach to software. So the way I like to think about this is we're printing some kind of metamaterial or lattice geometry that is so large, so intricate, that we wouldn't want to represent it all in memory or try and spin it around or even slice it and send it to a printer. So what we can do is actually work directly with printer hardware, and the printer hardware can kind of pull from the software. So the printer can say, I'm in position X, what do I need to know? And then the software will actually compute the geometry that it needs to execute that print at that time. And it goes along like this. So it's a tight loop between the software and the hardware. And so it's not quite real-time slicing, but this is just-in-time slicing, where as soon as you've configured your lattice geometry, your metamaterials, you can hit print, and your printer actually begins printing right away. So you don't need to wait for that file to save, to load, to slice, to send. All those things are eliminated. And so the result of this is that we are just printing more lattices, more surface area. Using this very data-driven meshless approach, we're able to eliminate that computational bottleneck. And the effect here is that we basically decouple resolution from build volume. So there's nothing about this methodology that would not scale to prints the size of a tank or whatever you might want to do. So I think this is something that we're really excited about, this idea of scaling up dramatically some of these amazing advances that are happening within research, but that are kind of stuck within a very small scale. And I believe that a lot of that work that the researchers are doing on carbon capture, filtration, and energy management, all these things are potentially highly relevant to not just kind of industry, but society at large. but that we need methods to scale up the production methodologies. So that's what we're really aiming for at Manifold. And if I can conclude with a kind of outlook or vision, my first point was just be that surface area matters, that we need to be thinking about, you know, the restrictions that are placed on what we are printing due to the way we handle geometry. And if we are able to handle geometry in a different way, we're able to produce more surface area, and this can lead to incredible applications. The second point is something that I've personally observed through years as a consultant, which is that often people think they want to design a lattice or design something, and what they actually need to do and want to do is solve some kind of engineering challenge. And that's really something that we care a lot about at Manifold, and we're trying to really bake that into our offering, try to make it possible for people to actually solve their engineering challenges. And then finally, as I already mentioned, you know, we're really interested in amplifying the research that is already being done by the engineering community on metamaterials. And we have an open invitation to anyone who is interested in collaborating to push the boundaries of that methodology. So we're really excited about that. And also just a plug that we are also looking for beta testers for our software. So if you are interested in metamaterials, lattices, please get in touch. I'd love to hear from you and start that conversation. So thank you for your attention. I'd love to take questions if you have them.
Thanks, Alyssa. That was super interesting, and we've got some questions coming in. The first one is, what additive technologies are you using to print these metamaterials?
Yeah, so that's a good question. So we prototyped a printer. Let me just go back here. Oh, sorry. Yeah, we prototyped a printer. It's what we printed this with. So this is a DLP-based printer that actually had a moving projector. So the projector slid along an axis, and then that's where the hardware feedback really comes in, because the hardware can say exactly what its position is and tell the software exactly what it needs. And so you can imagine this scaling up to, you know, either more projectors in an array or on linear rails as we had. So our approach was a DLP approach. To be honest, though, I mean, these prints were printed on an Anycubic printer, like a consumer printer, just using our software to generate them. But we see a lot of potential. I mean, so right away, our tech works with any DLP technology or MSLA, but we see a lot of potential for other types of AM processes. And so we're really excited about the idea of procedural toolpaths. We don't have a lot to say on that yet, but we're ambitious, and we feel like that's something that we can contribute to eventually. So DLP for now, MSLA for now, but other light-based techniques, and eventually a whole, hopefully a broader spectrum of techniques as well.
Great. What does the future look like for multi-material metamaterials?
That's a mouthful. Yeah. Multi-material metamaterials. Yeah, so I mean, it's funny, we did think about this actually in the context of batteries, because batteries, you need multi-material printing. And so what does the future look like? I don't know, but I think that there will be a demand for it actually because of batteries. So that's all I can say. You know, one of our decisions at Manifold was to focus on software, not on hardware. And I think that I would love to see someone take up the challenge in hardware of that. And I believe that our tech would have something to say on the software end for the multi-material metamaterials.
Great. Are you able to understand fatigue life of metamaterials?
Yeah, so I mean, that's something that is in the research domain. How do these things behave over time? And actually, one of the interesting things I can say about fatigue life is that we find that, and it's been established actually, that those stochastic geometries, like the Spinoid topologies and the other more randomly generated topologies, are much much better adapted because they kind of distribute the stress. Whereas the lattice topologies, you can get really interesting behaves, but the stress tends to concentrate at the nodes. So that's what I can say about the fatigue life for now. This is something that is an active area of study in the research domain.
Let's see. What's the print time for one of the metamaterials you showed?
Yeah, so because it's a DLP, we have been print DLP. I mean, DLP is just very fast, so it really doesn't take long. Trying to think, a centimeter is less than an hour for these things, so it doesn't take all that long. The large print I showed does take a while. I mean, when you introduce the moving projector, this slows things down considerably, and this is one of the reasons that we think that's not a key part of our offering, this moving projector idea, because it just does take a lot of time.
All right. What is the versatility of this model towards other AM techniques? Does that make sense? Can we use this method in power? Oh, I think maybe they meant method. Okay. What is the versatility of this method towards other AM techniques? Can we use this method in powder bed printing with fine powders, which actually affects the spreading of the layers? Does that make sense?
Yeah, so I mean, I think I sort of addressed this a little bit, that we're not working right now with methods that are not DLP, but it's on the agenda, and I think there's a lot of potential because of the way we handle geometry to account for things like other factors that come up in the manufacturing process. So you're talking about fine powders that have some effect on the layers. These are things that would need to be incorporated into the generation of the slice geometry. But I don't see an immediate issue with doing those sorts of things. But that's outside of my realm of expertise at this point in time.
That was our last question. Did you have any additional thoughts, Melissa?
Yeah, I mean, I would love to know from anyone watching just how you have seen metamaterials being used, and whether you've encountered challenges with them, and if so, what and where, sort of what industries. All these things are really useful and interesting to us as we're getting rolling with our software and our offering. So anyone who wants to reach out, please do. I'd love to chat further.